Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video we'll look at the linear model Perceptron, and we'll look at what a binary classifier is, as we already have seen that before. What is artificial neuron or a single layer perceptron, and uh, a notation, a mention of what is a feed forward neural network before we get into Jupyter notebook and do the actual coding. So a binary classifier is a classifier in which we are trying to separate two classes. So let's say we have a class, we have a data set, let's say with number of trees and altitude, and based on that we are trying to predict if that particular location gets rain or not. And that would be one type of classifier where this red line is able to separate these data points of clouds and sun. So this could be a positive class, and then this could be a negative class. Now in perceptron, let's look at this figure on the left hand side. So that's an image of a cloud, and each of those squares is 1 pixel. So each of those pixel is input as a feature to this neuron that's shown here on the right hand side. So the gray value of, or the value of each of those pixels is multiplied by the weight, and that's the input to the neuron, and that is done for the entire image set. So in this case we have total of 169 pixels, and all those would be the features in that particular data, features for this particular neuron. Now the neuron computes an output value, which is then classified based on the score. So let's look at this slide here. If the score, which is wx plus b, where b is a constant here, if that is greater than 0, then that particular class, then it is then that image is assigned to class 1, which is clouds, that it will rain, and otherwise it's assigned to class 0, which is sunny, and it won't rain. So basically we can go from an image using a neuron or perceptron to classify that image to either a positive class or a negative class. And in doing so, what this is an example of is a feed forward neural network, a very simple one. What a feed forward indicates here is that there is no feedback loop from the point after the neuron to update the weights. So it's that would be the backward propagation, which does not happen here. So the information flows only in one direction, and that's a forward direction. So that's the takeaway message from this slide. In the code snippet, we have this is similar to what we have been seeing. uh, Here we are importing numpy, linear model, and then standard scalar make pipeline. And to this train and test data set, we first pass it through the standard scalar in the pipeline, and then fit the model using linear model.perceptron as shown here. And uh, this is fit on the X train, Y train, and then finally use the clf.predict to predict on the test set. Now let's get into Jupyter Notebook and look at the code. So these are the libraries that I have imported. There are several libraries here, and this is the version that I'm using. You may have to pause the video to note which of these libraries are used, and these are the versions. Now for the augmentation step, in this data set, in this video, the data set that we are going to use is a data set with two types of images, clouds and sun. I've handmade this data set, and I've uploaded it on GitHub, and I'll post the link below in the description so you can download it. Additionally, this is the function that we have discussed in the previous video for image augmentation. It's the exact same function. I'll also put a link in the description for this function so you don't have to type it. With this set, we can now go ahead and perform the fit first on the data that is not augmented, and then on the data that is augmented. So let's look at the data first. And here because I've already downloaded the data, it's at the path which would be different on your computer based on where you have saved it. I've saved it on the desktop, so this is the path that I'm navigating to. Now with this, the what I'm going to do now is initialize. So initializing a list for images, then initializing a list for the output labels y, and then using a for loop to read the images. So reading all the images from the folder that I've downloaded. So file in os.listdir path. There are different ways to read it. So this is using the os.listdir, and I'm going to read each image, save it in the temp folder. So temp variable. So io.imread os.path.join, and then this is going to join the path and file name, and I'm going to read it as gray image, as gray is equal to true, can spell true, and then this needs to be reshaped. So I'm going to reshape it to 1 and -1. Once this is read, this I'm going to append this image to the empty initialized folder image above, and finally add the class label. So the class label is based on the file name. So if the file.split, so the file has the string of the file name, is split using the underscore, and then if you take the first part of that, if that is equal to cloud, then it is we are appending 1 because it will rain, so the label is rain, and therefore we have the label as 1. Else we are going to append 0, uh, suggesting that it's not going to rain, so the uh, image would be of sun. And once that is done, so let's run that, and now we can let me put that in the same cell. X is equal to np.concatenate, and here this is images, that's the image, and axis is equal to 0. So what I'm doing here is concatenating all the arrays that we have in the list image. So if you have this is there are 200 of them. So if you look at this, these are different arrays, and now after concatenating, we have this as the shape of the array. So there are 200 rows and 4096 columns. Each column is 1 pixel, so entire image is flattened out as 1 row in this particular case. Now let's visualize this. So visualize, and for visualization I'm going to print this print y 0, and so that's the label that we have. I am show and x of 0 dot reshape. We are reshaping this as 64 by 64, and as you can see, so that's the image of the sun. And apart from that, we can also plot another image. So I'll copy this to speed up the typing. And now let's look at 4. So 4 is image of a cloud, and next we are going to do a shuffle split on the data set that we have. So shuffle and split, and what that will do is we'll get the X train and Y train. So X, Y is equal to shuffle X, Y random underscore state is equal to 0, and that is important so that we don't have the sun images lined up and cloud images lined up when we are doing the split. So for split we have x underscore train, x underscore test, y underscore train, y underscore test is equal to train underscore test underscore split, and then we have x comma y, and again random underscore state is equal to 0. So here we can go ahead and print x underscore train dot shape. So we know how many records we have in the train data set, and then we can print x underscore test dot shape, and that will tell us how many records we have in the test data set. So we have around 150 records or 150 rows. Now let's go ahead and fit the perceptrons. So we'll do that using Perceptron, and this is now, so far we haven't used the augmented data. So for this we need to normalize, so we'll start with pipeline and then use the fit. So CLF is equal to make underscore pipeline, and here we'll use standard scalar, and then we have linear underscore model dot perceptron, and we'll use tolerance of 1 e to the power minus 3 random underscore state is equal to 0, and then use clf dot fit x underscore train y underscore train, and so that's the train part. Then we can predict and score, so those two parts. So y underscore pred is equal to clf dot predict x underscore test, so we predict based on the test set, and then you can get the accuracy matrix dot accuracy underscore score y underscore test and then the y underscore pred, and then we have the accuracy. So we are getting 1 as accuracy, and that's uh, we won't it's difficult to get a complete accuracy, but maybe just for this example we got lucky to get 100% correct predictions. So we can also get the confusion matrix. So matrix dot confusion underscore matrix, and here we can specify test y underscore pred, and we can see that 22 out of 22 are correct, and all, so the diagonal off diagonals are 0. It means all the predictions are accurate. Now let's look at using the augmented data and see uh, how that works. So for augmented data we already have created the function, so I won't be going through that function how it works. Basically it just creates 15 images from one image. Now to use that function we first need to set the path. So path is equal to users, this would be the path to the directory where that image is, where those images are stored, the original images, desktop, and then data, and here I'm specifying star.png and xay, so these are the empty lists that I'm initializing, and then for file in glob.glob, so here we are going to go through the directory, read each file, and then put that in here after augmentation. So augment image, so that's where we call that function that we have created, and then xa.append tx, and then ya.append ty, So we append the augmented values, and then we flatten the uh, lists within the list by a list comprehension. So for j in I, what you want to do is j for I in xa, and similarly we have y is equal to, for j in I, uh, this would be for j for I in ya. So for we are, what we are doing here is, let's say if we have a list within a list, so 1 comma 2, and then we have another list 4 comma 5. So we are flattening this and converting this to 1 comma 1 comma 2 comma 3, sorry, 4 comma 5. So that's what we are doing here with when using xa and y. Now once we have run that, let's see if we get any errors. If not, then we'll print the length of this, so length of xa, and then print length of ya, and both of those lengths should be similar. So now we have 3000 3000 data points, additional data points, and to this will add the original data point. So new x that we have now will have 3200 images. np.concatenate, and here within a list we specify the earlier value, and then concatenate. These are the new values that we have. Axis is equal to 0. So this could have been done in separate steps, but I'm just adding them together here. So that's the new x, and for new y, we have y plus ya, and thus if we print the new x and the shape of new y, so shape of this, and then print new y, so this would be length of new y. So we get, there are 32 rows, so 32 images, and each image is 64 by 64, therefore 4096. Now with this perceptron we can perform the fit. So perceptron, and here we have, first we do the shuffle. Shuffle is new x, new y is equal to shuffle new x, new y, random underscore state is equal to 0, and then again we are going to do the split train and test. So here is split x underscore train, x underscore test, y underscore train, y underscore test is equal to train underscore test underscore split, and this is based on the new x and new y. And finally we can do the fit using the pipeline. CLF is equal to, let me go ahead and copy that so we don't have to type it. Copy, and I'm just simply going to paste it here because it's the exact same stuff. And then predict. So for prediction, again, it's the same stuff. Y underscore pred is equal to CLF dot predict x underscore test, and then x underscore test underscore test, and then we have score. So for score accuracy, so matrix dot accuracy underscore score, y underscore test, y underscore pred, and we can compute the accuracy here. When we run this, we get an accuracy of 1. So this is with the augmented data. Now we can get the confusion matrix. So CM is equal to matrix dot confusion underscore matrix y underscore test, y underscore pred, and here we'll first create the matrix without any class names. So figure x is equal to plot underscore confusion underscore matrix, and this is using the ML extend library. Conf underscore mat is equal to cm, and when we run this, this is the confusion matrix we have. The off diagonal elements are 0. Now to add class names to this, if you notice in this confusion matrix, the 0 0 is the top left corner and the 1 1 is the bottom right corner. And so we know that class names for rain and no rain, so rain is 1, so therefore class names is equal to, I'm going to specify rain as the, so no rain would be the second one, sorry, no rain would be the first one, because we are looking at 1 for rain, so 0 and 1. And because we have class names, we can now specify the class names here is equal to class underscore names, and when we run this, this is the confusion matrix that we get. So 404 are correctly predicted as rain, so those with the images for clouds. And we can also double check that by looking at the sum of ones and zeros in the y pred. The y underscore pred is equal to 1. If you look at the sum of that and the 1, so this is 404. So that's equal to what we have seen before for the correct predictions of the cloud images as compared to the sun images. That was it for this video. I hope in this video you learned what is data augmentation and how it is used with the perceptron neural network or feed, one example of single layer neuron. And in the previous video understood what data augmentation is. I hope you are able to apply this knowledge in a data set that you can create on your own and see what results you get. You can also try to apply this on the imaging the MNIST digits dataset using datasets.load underscore digits. I hope to see you all in the next video. Please like, share, and subscribe. And if you have any comments, please let me in the comment section below. Thank you.